This is a great question because we're actually moving on to calculations. So here, this is an adiabatic process, and here's what we're assuming. We're assuming that we're doing work to change the internal energy of an object. So we're going to actually do this work, and what it's going to do is it's going to change the internal energy in the following manner, according to the formula mc delta T. So I do 1 joule of work because this is the force and this is the distance. So I can say 1 joule is force. So again, work, I'll say it like this. Work is force times distance. That's going to be 1 joule times 1 meter, which gives me, 1 newton times 1 meter, which is 1 joule. And that's going to equal mc delta T. So let's get that temperature change. So I've got 1 joule equals, I've got 5 grams here. C is 0.51, and delta T is going to be T final. You know what? I'm going to just calculate delta T like this and then add it to the 23 at the end. So when I actually do this, this is going to be 1 divided by 2.55. And when I actually get this, 1 divided by 2.55 is about 0.4 degrees Celsius. That's all well and good. Now let's be clear. This is for 1 bending of the coat hanger. Imagine, now if you repeat this process, say 50 times, you're going to be changing your temperature by about 20 degrees centigrade, which is 43. But we were doing it like 80 times, so we're talking about closer to 40 degrees, so we're getting up there in the temperature. Remember, water boils at 100 degrees Celsius. So if you flex this coat hanger 40 or 50 times, you've already brought it to the boiling temperature of water, just to kind of put that out there. So, oh, I love this essay that I wrote. This is me just sneaking on. There's a lot of words here, but let's just kind of, as a teacher of mine once said, when all else fails, follow the directions. So the refrigerator form of the second law of thermodynamics says that it is impossible to move heat from low temperature reservoir to high temperature reservoir. When all else fails, learn how to write your test, just that repeating stuff. Meow. Okay. See, I can turn my sass on myself. Okay. A simple way to state this is that every refrigerator requires a power source because it won't spontaneously cool your food down. Okay, cool. So now, what we're trying to say is that if this is true, the engine law should also be true. So we're supposed to prove this, that one implies the other. All right, so he says, assume that the normal refrigerator law holds. Okay. So what I'm going to do is show this with an illustration. So I've got high temperature, and I've got low temperature. And I'm going to build a little refrigerator machine, and here's what we'll do. We'll assume that we have to take in a little work, and we'll assume that a little heat passes up here. And so what's going to happen, so we got a little heat coming up here. And what we're assuming is we draw heat from the low temperature, we do some work with the, so here's the electricity source. So this is like our power source, right? This is our food that we're trying to cool. The power draws the heat out of the food. And then what gets moved into our environment is heat plus work. To be clear, what we mean by environment is the kitchen. Like in real life, this work represents you plugging in a refrigerator. And then what happens is heat is sucked out of your food. And then what gets put out into your kitchen is warm air. It turns out refrigerators actually heat up their surroundings. They take the heat extracted from your food plus the energy that was used to power it, and it throws all that out there as wasted heat energy. Well, not wasted because the food's cool, but then that heat that we throw out, we can't get any more use out of. All right? Now, what we're saying is assume that we have a perfect engine, and that what this means is that you can, in fact, power our perfect refrigerator in a way. Here's what we're trying to say. This is an imperfect refrigerator. Our claim is if you are allowed a perfect engine, it's possible to build a perfect refrigerator. And that can't be true. So if a perfect refrigerator isn't true, then by extension, we can't build a perfect engine if it allows us to build a perfect refrigerator. So here's the idea. Now let's take our perfect engine. And I'm going to assume one small thing. Let's just assume that work is less than the heat that we're trying to put in. And here's what we'll say. Now let's allow a perfect engine. So I'm going to take a high temperature reservoir, and I'm going to take an amount of work equal to, I'm going to call this Q 1, and I'm going to set it equal to the exact amount of work that I want to power my refrigerator. So I have my engine, and it's going to spit out this Q1 that's equal to work, is to convert all of that Q1 directly into work, and absolutely nothing goes into the low temperature reservoir. Here's the machine I'm going to build. I'm going to take my perfect engine, I'm going to let it put out this work W, and then what I'm going to do is I'm going to let this work power my refrigerator. Okay? And remember, we're drawing up an amount of heat Q1 from our low temperature reservoir going into my high temperature reservoir. Now check this out. I've got work Q1 going up, and then check this out. I have the work going in. So I'm receiving Q plus W, and I'm sucking out work Q1. So the total amount of work that gets dumped into the high temperature reservoir is going to be Q plus W minus Q1. But Q1 is exactly equal to, and sorry, this should be Q1 down here. So because I'm taking, sorry, let me start this again. I'm taking energy Q here and energy Q here. Yeah. So the total amount of energy that goes into the high temperature reservoirs, I'm sucking out Q1, so it's minus Q1, and I'm putting Q plus W into it. So the total amount, I have Q plus W, which I said was equal to Q1 minus Q1, and so I'm actually I'm actually getting a total amount of work Q put into the high temperature reservoir. What does this all mean? It means that if I put this thing in a box and don't open it, okay, if I have a perfect engine, it turns out if I use a perfect engine, I can suck out the heat from the high temperature reservoir and then dump it back in there along with this and get something for nothing by doing this work. So what ends up happening is this machine is effectively a machine that takes Q from low temperature and puts it into high temperature. All right. So and we just said that that's impossible. So what that means is if you allow me to build a perfect engine, I'm allowed to build a perfect refrigerator. So that's not going to work. So by kind of a proof by contradiction, perfect engines can't exist either. So that's one part of the thermodynamics calculations. Let's finish this last one. Let's get the entropy change, just like we did in class. So I have 100 joules taken out of the 200 reservoir, and then only 80 of it goes into the 100. So this is for A, the total entropy change. I'm losing 100 joules of heat from 200, and then I'm putting 80 joules of it into the 100. So I'm actually getting negative 100 plus 80 over 100. So let me just get a common denominator. That's 180 over 200 plus 160 over 200. That's going to give me 60 over 200, which is 30 over 100, which is 0.3 as my entropy change. By the way, if you want to know what the units are in entropy, it's joules per Kelvin, but I'm not going to emphasize that on the test. The actual efficiency of the engine is the 80 joules. So I only do 20 joules worth of work. So 20 over the 100 joules that I take is the actual efficiency. That's 20%. Versus the Carnot efficiency, which is 1 minus 100 over 200, which is 0.5, which is 50%. All right. So this is the third problem that we're working on. And so I think that actually wraps up our thermodynamics portion of the test.